Hi, everybody. Happy Friday. What's the temperature outside right now?
Too hot.
Too hot. Well, still February, isn't it? Selwyn Heminway is here, going to talk about beach erosion, dune erosion. It's very interesting. I already saw her slides, but didn't hear what she had to say yet. So everybody, let's welcome Selwyn.
Okay, so welcome to my brown bag. Like Linda said, I'll be talking about modeling dune erosion on the Outer Banks of Australia. Okay, so if you pay attention to the news, you might have seen this headline last winter, in February, when 2 houses in Rodanthe, North Carolina, actually just fell into the ocean, likely from the beach erosion and continued inundation, probably from climate change. Now, a little tidbit about this story: the guy who owned that black house, I read, did not believe in climate change. So it's a little bit of a rude awakening for him on that part. But we're seeing cases like this today, but it's only going to get worse with climate change. And climate change is exacerbating coastal hazards in 2 ways, in which I'll be focusing on in this presentation. First is sea level rise. Now, this is a map taken from the Coastal Flood Exposure Mapper website, which is a pretty cool website. You can add different GIS layers of what the effects of climate change is going to be. I'm sorry, there's no scale bar or north arrow, but I didn't make this map. So this is, it's of downtown Norfolk, which is just, southeast of us. We're up here in the peninsula in Williamsburg, and then to orient you, this is Virginia and North Carolina border down here. And everything that you see in blue is totally inundated. That's where the water is right now. And I'm going to walk you through what it's going to look like at 6 feet above mean high water, which is around 2 meters. And that's the most extreme case of sea level rise that we're predicting to see. Not that I know is predicting to see it by the end of the 21st century. So here we have, okay, well, there we go. Here we have up to 2 feet above mean high water, which is, you can see like some of the marsh is inundated, it's creeping up on some of the roads. But then when you get up to 6 feet of mean high water, above mean high water, it's a lot of blue. There's a lot of inundation happening. You can see it's kind of overtopping these roads over here, and it's going to displace a lot of people. People are going to have to abandon their houses and will probably be considered climate refugees. And this is not just happening in Norfolk, though this is one of the fastest places of sea level rise in the US, but it's also happening globally. So this is a really important and serious problem that we need to study to kind of see how we can mitigate the effects of sea level rise and be prepared when it does inevitably happen. The second thing I'll be focusing on is storms. So climate change is predicting to bring more intense and frequent storms from that interaction of the warming of the ocean water and with the cold air. Not an expert on how storms work, but it's gonna get more intense. These pictures are from the Outer Banks from Hurricane Irene. And you can see in this photo, all that fast wind and waves, it just completely breached the entire island, which is a huge issue. This is the road here, and it was broken apart in multiple places. This is another view of the effects of Hurricane Irene. They tried to put some sandbags up here to prevent the coastal flooding and storm surge, but they don't work as well as dunes. So, obviously this road does not look very good. So coastal communities rely on dunes to protect their low-lying infrastructure from these coastal hazards. You're looking at a coastal forwarding right now, and it's defined as the topographic high directly landward of the ocean. And it often works as the first line of defense against storm surge and ocean flooding. And I want to bring your attention over here to the mean sea level line and the storm water level line. The mean sea level is kind of where it is on a daily basis. It's between the high and low tides. But when storms come, it brings a really high energy system with fast winds and high waves and the winds are actually pushing that water up onto shore and increasing the mean sea level. And so when the storm water level interacts with the dunes, there are a variety of things that could happen. Mostly dune erosion, but we're trying to figure out, what the unknowns here is what is going to happen to the dune once the storm water level the elevation exceeds the dune toe or even overtops the dune crest, depending on how high sea level is going to get. So the first dune behavior that we could see is dune erosion. And that's when you see the water level is going over top the dune toe elevation, and those waves are interacting with the dunes. And when the water infiltrates the dune, it creates a lot of instability and can often lead to slumping, which is kind of when a bunch of sand just falls off and gets taken back into shore. And here you can see this area is what has been eroded in this schematic. Now, the second process is dune accretion, and it's mostly driven from aeolian sediment transport, which is wind-driven erosion or wind-driven sediment transport. It's when there's strong winds, it picks up a lot of sand grains on the beach and moves it into the dune. And when the wind hits an obstacle, such as vegetation or sand fences in a different scenario, it slows down the wind and allows the sediment to drop out onto the dune. And so here, kind of similar, this shaded area is the volume change. So, but in this case, it's the dune is accreting upward, moving the dune toe out and the dune crest up. So we're trying to get at the interactions between the aeolian transport and wave erosion during a set period of time in our models. And so that leads us to the research questions. One is, how will coastal foredunes respond to increasing sea level rise and storm intensity in the Outer Banks, North Carolina? And two, will dunes respond differently for varying beach states? We'll be testing the hypothesis increasing sea level rise and storm intensity will lead to more erosive foredune systems than the modern day. And we'll be doing this with the AOLIS model. The AOLIS model is a cross-shore dune evolution model, and it basically works by simulating a lot of physical processes that are happening between the beach and the dune. So, for example, it's the wind-vegetation interaction, aeolian transport, which I just kind of talked about, leading to dune accretion, bed elevation change, sediment vegetation interactions, all that good stuff. And this is a really great tool because it can be applied to case studies across, the world, I guess, across the coastlines. And for my project, I'll be applying it to the Outer Banks, where I'll be putting in the site conditions, such as the morphology and the wind, wave, and tide data that is specific to the Outer Banks, and then testing these alternative scenarios, such as different climate states, and then I'll get into the other next steps later. But okay, so first is morphology, which for those of you who don't know, is kind of just the shape and the dune profile and the beach profile. And so those shapes, the beach and dune morphology varies across the coastline. These are 5 photos of dunes that I took over the summer when I was working in the Outer Banks for my research. You can see they don't all look the same. There's a lot of variation in what the dune looks like in the beach slope. Specifically over here, if you just compare these dunes, this is a really small dune with a pretty steep beach compared to this is a really big dune with a pretty flat beach. So those dunes are going to interact differently with storms and sea level rise. To account for this, I'm using a range of dune toe elevations and a range of beach slopes, which you can see down here. What I mean by dune toe elevation is kind of where this dune starts, and then the beach slope is the overall average slope of the beach from the dune toe elevations to the shoreline. Now, the second input that I'll be using, I guess second, third, and fourth, is our wind, wave, and tide data taken from the Outer Banks, North Carolina. And here's a little photo of where it's being collected. This is the site of the Army Corps of Engineers Field Research Facility in Duck, North Carolina. And, the wind, these three inputs have been continuously collected since I think the 1980s, I want to say. And so, there's a lot of data here that we can utilize for our modeling. Out here, you get the wind speed gauge at the end of the pier. The wave monitor is more offshore. And then we have the weather radar antenna on the actual building. So here's what the time series actually looks like. On the x-axis, we have days. So time starting from 0 to 364 from January 1st to December 31st. And on the bottom panel, we have tide elevation, and you can kind of see those daily fluctuations of tide. And then the wave height in the middle panel varies throughout the year. It's very low in the summer months, so not very good for surfing. But then again, it's kind of variable in the fall when it becomes more of hurricane season. And then the wind speed up here on the top panel, there's a lot of variation throughout the year, though there is a bit of an increase in the fall. So we chose the time series from 2019 because it's the most recent and most comprehensive set of data that we have, and it also includes the Hurricane Dorian that hit during August 24th to September 10th in 2019, and that allows the model to actually have a real life hurricane to incorporate into the processes, and kind of it's great for our purposes because we're trying to figure out how storms affect dunes. So I'll be taking those site conditions and then changing the wind and wave titles based off of different climate conditions in two different ways, again, with sea level rise. Sea level rise is pretty difficult so it's difficult to nail down a concrete projection of it because there are so many different physical processes that are affecting sea level rise, but specifically the main key ones that are causing the numbers that I'm looking at are the thermal expansion of the ocean water and then the land ice melt and discharge. Those are the key ones driving global climate or global sea level rise. And we took the numbers from a NOAA technical report released last year, having 5 different scenarios for 2100. And you can see here, we got 0.3 meters to 2.0 meters being the low to high scenarios. And we incorporated sea level rise into the model by just adding a uniform value to the tide time series. So if we go back and look at the time series, down here where you see the daily fluctuation of tides, it would really just be shifted up, a uniform value, whichever one we're choosing, if it's 0.3 meters to 2 meters. So next, I will be incorporating storms into it. Again, there are a lot of variable predictions that you could, model with storms, from the increase in frequency, the increase in intensity, precipitation, even the change in tracks of the hurricanes. But what I'll be focusing on is the increase in storm intensity. And when I say increase in storm intensity, just kind of means storms are going to get worse. They're going to have higher wind speeds. They're going to have higher water levels, like resulting from storm surge, and also just, higher waves too. There's a lot more damage that's going to come from storms. And it's even more important and scary too, because storms, at the same time that storms are getting worse, the sea level is also rising. And so that background water level is going to be even higher, and then increasing the storm surge even worse with the worst storm. So anyway, it's going to be bad. So we're incorporating storms into the model in a bit more complicated way than sea level rise. We identified the top 10 storm events in 2019, and then we chose the maximum value for each of the time series, and we amplified it by a certain percent. So this is the red shows the new time series for 50% amplification. You can see over here in hurricane season, it's pretty clear how much those storms are going to be increased. I just threw a lot at you, but those are all of my inputs into the models, and there are a lot of moving parts to this project, so I'm going to walk you through it. This is more of a comprehensive table of the variables that I'm using. first, I'm testing morphology. And so I took these 4 dune toe elevations and 4 beach slopes and combined them into 16 different morphology. And so basically 16 different types of dunes that I'll be testing here. And we're first doing it as kind of during modern day conditions to get a bit of a baseline of how they're behaving during the modern day, and then we'll add in the climate conditions later. So this is a matrix of my data and the volume change that we modeled, but I'm going to walk you through this because it's kind of a complicated figure. When I first saw these figures, I thought that the blue meant the water and the red meant the land, and then, you know, the black line is the waves. That's not it at all. So wipe that from your brain. On the x-axis, it's the dune toe elevations. So it's 2.5 to 4. And then on the y-axis, it's beach slope from 0.05 meters over meters to 0.15 meter over meter. And then the red area represents erosional behavior, while the blue area represents accretional behavior. So for example, if a dune was plotted up here in the top left corner, then it would have a lower dune toe elevation, say around 2.6, and then a steeper beach slope around 0.14. And it would look like this. These are the profiles that I'm actually looking at once the model is run, and kind of how you can visually see what's happening. On the x-axis, it's the cross-shore distance from the shoreline. And so it's kind of opposite from those schematics I was showing you earlier, but the ocean is over on this side, and then you see this dune here. The black line is what the dune looked like before the year-long simulation, and the red is what it would look like at the end. Now, there's not much dune left at the end of this simulation, which is one of the ones that had a massive erosional behavior. Alternatively, if there's a dune plotted over on the right bottom hand corner, it would have a high dune toe elevation and a gentler beach slope, and it would experience net accretional behavior, which would look something like this. Again, cross-shore distance on the x, elevation on the y, and the black line is the initial profile, and then the green line is the final profile. Now, I know this looks a little wonky. This is not what it would, you know, realistically look like, but we have this spike here because that's where the model is basically putting the vegetation. And so that's where the sand is being trapped in the model, and that's where we're seeing that the most accretion happening. So before we move on, are there any questions about this graph? Because this graph is super important to my work. I'm showing all of my results with this graph, so I want to make sure everyone's with me. Yes.
The black line comes from the 15 possibilities.
So the black line, I might not have said this, the black line is the threshold between the erosional and the accretional dunes. And so if a dune is plotted somewhere along that line, you know, there's going to be more of a question of the stability and the resilience that it's going to have. But if it's plotted in the red area, it's going to be really vulnerable to climate change and sea level rise. And if it's plotted in the blue area, it's going to be pretty resilient. Yeah.
Does it tell you anything about the elevation or slope, or does it just the volume of the sand?
Yeah, it's just the volume change. Yeah. Yes.
Over what time is this happening? Like, is it over those like weeks of data, or is it like for multiple years?
It's just over. It's over 1 year long period. I'm using the time series that I showed you in the previous slides. Okay, so the main finding from the modern day conditions is that lower dune toe elevations paired with steep beach slopes lead to higher dune erosion. So that is referring to all this red over here. So now that we know how these different morphologies are reacting in the modern day, we're adding the variable sea level rise to it. And we're only using 4 of these scenarios. In the last slide I showed you 5, but we're taking out 2 meters because when we started modeling 2 meters, it really just resulted in almost all of the dunes being completely eroded. So we didn't include it in our data analysis. So here's this modern day condition again that I showed in the slide two slides back. And then we have the increase in sea level rise gradually from here, from 0.3 to 1.5 meters. And we found that there's an overall increase in sea level. Any overall increase in sea level enhances dune erosion. And you can also see this downward shift of the accretional and erosion threshold towards the bottom right-hand corner. So that is really bad because that means that a lot more dunes are going to be vulnerable to erosion when this shift occurs. And I want to point out the magnitude of volume change here. So the darkest red, the most dune volume change that we saw was 80 meters cubed per meter. And if you visually kind of think about what that looks like, however big a meter is going to be like a meter by a meter by a meter over every meter. So that's a lot of sand being eroded. But then the highest accretion we saw was only 6. It was only 6 meters cubed per meter. So there's a really big difference in the magnitude of what is happening here. Now I want to focus more on the storminess now. We again saw that downward shift in the threshold, but it is not as extreme as we found with sea level rise. And it led to overall less erosion than the sea level rise scenarios do. I also want to bring your attention to these darker areas in the high dune toe elevations. It does appear here, even though it doesn't look like it, but trust me on that. I looked at the numbers, not the shading. But that darker blue shows that there's actually more accretion happening on those dunes during increased storminess conditions than modern day conditions. So even though it is bringing overall more erosion from modern day to increased storminess conditions, it also indicates a potential accretional abilities of storms under specific morphologic conditions. So we tested sea level rise and we tested storminess separately, but in an actual climate, in our real world, we're not going to have one without the other. So we combine them into 2 different climate states. One, as the low risk climate, and that one is the high risk climate. And we use that 5% increase in storminess because that, like I mentioned earlier, that's the most common prediction by the end of the 21st century. And then we use the 0.5 meters of sea level rise for the low risk and the 1.5 meters sea level rise for the high risk. This is what we found. There's a lot of red here. So the low risk climate, to just remind you, the threshold for modern day was, about here. So we still saw that downward shift in low risk climate, but that's basically our best case scenario here. And it's still not looking too great. But then when you get to the high risk, almost all of that is a lot of dune erosion. And from this, we can also kind of conclude that sea level rise is going to be the main driver of dune erosion as opposed to storms. Because if you think about it, we didn't change the storminess conditions for these 2 scenarios, but we changed the sea level rise. And so that's what's going to be the most important thing to take into account when predicting dune behavior. So some key takeaways from my research so far is that sea level rise is a greater threat to dune stability than storm intensity. Increases in storm intensities resulted in more variable dune growth. Smaller increases could generate dune growth, while variable increases could generate higher dune erosion. And then finally, the climate response is dependent on pre-existing dune morphologies. Now, we know how climate change, or how storminess and sea level rise are going to affect the dunes, but now we have to be asking more of a management question, such as how can we mitigate the effects of climate change on dune behavior? These are 3 kind of management strategies that you see along coastlines almost everywhere, a lot over the East Coast, but specifically in the Outer Banks. Beach nourishment is when you dig up sand from offshore and then you pump it onto the beach using this big pipe. And then you actually manually increase the beach width, which is a lot of work and very costly. so not ideal. But then we have vegetation plantings. This vegetation is natural. I don't have a good photo of the plantings, but when managers come in and plant grasses, you're going to have a grid with grass planted, in a pretty symmetrical way. And that's to enhance the sediment trapping in the dunes and hopefully help them accrete. And then similar with sand fences, when you install the sand fences, a lot of the sand is going to get trapped there, and that's also trying to help the dune accretion. So I've done the morphology, I've done the wind waves, and I've done the climate stuff. And now we're going to be incorporating the sand fencing and grass plantings into the model and kind of seeing if those management strategies and varying them will change how the dunes evolve over this year-long period that we're testing. And that can kind of get some concrete recommendations for managers, which is pretty exciting. And it actually might, be taken into account of how they're actually going to start managing the dunes and Outer Banks. We'll see though, that's the hope. And so I'm asking, how can we optimize sediment trapping on dunes using sand fences and vegetation? Over the next few weeks, we're already working on the model runs, so hopefully that'll be done soon. Check back for my honors thesis if you want to hear the answer. So I want to acknowledge my advisors, Chris Hine and Nick Cohn, my mentor, Liz Davis, the FRF staff, especially Janelle for helping me with my coding issues, and the Coastal Geology Lab, and my friends and family, especially the ones who I made listen to this talk before today, and the funding opportunities that have, helped this project along the way. I'm going to leave it on the key takeaways, and I can take any questions.